seems to do something. Needs to be filled with something. Okay. What's in my plan today? I would like to tackle one problem. What if, let's say, we have a linear system? What can be characterized with transfer factors? It has input signal and output signal. It's okay, it's fine. What's this? Yeah, it's a linear system with input and output. Characterized, what can be characterized with its transfer characteristic or simple factor. What if I take output to another system? Let's say it can be described as a beta. And send it to the, for example, some function, to my first system input. What if I'll try a closed loop? How? Draw it. Here is the addition function. What if I return output to the input?
Then it's a loop.
Yeah, it's a loop. How will it work? Yes. Who and why? Ну, это я позже, я сейчас у меня тут занятия, я после занятий найду. Да, окей. Да ничего. Okay. So I have, let's assume it's linear. I have linear transfer active and return with some characteristic. First, I would like to tackle this part. How can it be? What's a linear transfer stage of this linear circuit? Previously, we spoke on circuits containing active resistance, inductance, capacitance, mutual inductance. All these elements were assumed linear, what means? None of the parameters, neither resistance, neither inductance, neither capacitance, neither magnetic coupling, were dependent on voltage or current. Fine. I would like to extend area of linear circuits. All the circuits were passive, meaning what energy amount in them decreases. Active resistance means what circuit is dissipative. So if I supply pulse from my pulse generator, process goes to decay because energy amount decreases. Now I need more. I would like to introduce one of the first ideas in this area. I need active but linear. Here I have one demo object. I may make it bigger. One moment, I will get my demo object. Here is my demo object. It's called triode. It's a vacuum bulb with 3 electrodes. Number 1, can I switch it on? Oh, here it's close, it's hot. It's called cathode. So I have energy source here and it's grounded. It's a cathode. Anode or plate. Here I have. Maybe I switch. Sorry, I want to switch this off. Now it's, I hope you can see it better. Here on the top is a plate or anode and grid. Here I have grid. Ampere meter. $250 volts. Ground. And here I have source a ground. What will happen if this one is hot? Here I have positive voltage. It's A. What will happen? Electron will leave hot cathode and travel towards plate or anode because it's static field. Faster. I'm speaking about linear circuits. Now it will be active. So, how will it work? Here I have nice example. Hot cathode, grid, and cold plate, but with high tension on it. Maybe even, okay, 250 is okay. So, how will it work? Electron leaves and passes through grid. If grid has positive potential, electron will be, how to say, pushed up, yeah? If negative, what will happen? It will be pushed back towards который. Here I have 2 meters. I hope you can see my 2 meters. This one measures grid potential. Lower one is EGA. This one is here, and plate current and plate current. Tiny problem. Yeah, I had a parallel resistor not needed here. And this one is a plate current, this one is grid voltage. Grid voltage now minus 52 volts, all electrons are pushed back, so plate current is 0.
So all electrons are pushed back.
Yeah, pushed back towards this. For a moment. Put this away, take this away. So all electrons are pushed back to cathode, towards cathode. Look. I can increase voltage. Minus 43, minus 20, minus.
Okay.
Come back. Minus 4.7, you see, small current. Alright. Bit higher, 1.2 volt, 3.9, 4 volts. So, no more growth. You see what I'm saying? 0, current appeared, and no more growth. It will not grow over 175. What do you see? Current in circuit. So this current is dependent on the grid voltage, yes? I can draw nice chart. EGA, anode current. And it will look something like this. It has small decay at very high voltage because plate potential is less than grid potential. Grid will act as a plate. Grid will catch electrons. I will see grid current. See? Negative voltage, no current. At a 0, let me catch, where's the current? Minus 10, no current. Minus 7, no current. Minus 1, oh, we have small current. 5.6, 85. Plus 14, 147. Plus 20, 169. 172, 175. no more growth. After 40 volts, nothing grows. So, bit more correct will be to draw it like this. I have linear part here in this area. Current is proportional to grid voltage. And then saturation. What will happen if I add some signal to the grid? Signal. Here is my signal. Oh.
Add signal to the voltage. You mean?
I mean, yes, it's where are you? I'm here. 1 second. Yeah. Here. Signal is an AC voltage. Oh, this nice yellow voltage. What if I put this nice yellow voltage what will happen? What your phone telling you? I see you're not interested in my course.
Oh, yeah.
Yeah, this thing is named DOE. Let's say I'm in the time T1. I should mark here T1. What will happen? This is T1, okay. This is 0. 0 corresponds to 0. What about this point? T2. This one, T3. And here is my T4. Do you understand how I created this
Yeah.
chart? Current follows a voltage. Yeah? And now, what I will do, I will assemble network. I know the resistance. My well, through capacitance, this is Sx. Resistance. And here will be and through capacitance Sy. if current changes according to voltage, can I show my valve as a resistance, let's say Ri, being controlled by a gun in limited area, in this linear area, not everywhere. What will be output voltage? I have a divider. Here is the divider. Huh? Divided L plus Li and multiplied by Li. So output voltage will be input with some proportion, with some rating. Watch it. I'm changing offset. I'm changing work point. Oh, of course. Nothing. I'm raising voltage, 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 voltage. Clipping, not good. Oh. I'm in linear. I'm in this point of characteristic. Because I'm not, this chart is here. I'm not able to use it fully. I have clipping. I'm moving the changing a gun is like shifting this chart. Well, I may show it in green. It's my work point. It's a 0 point. With the change of voltage, I'm moving. Now it's at the beginning of characteristic. I have clipping in the middle and in the saturation area. I have soft clipping on negative side. Here I'm in linear area. And what do we see? At the input I have 1.6 volt. At the output I have 12 volts. You see what characteristic they repeat each other, but it's negative. At this moment, my triode or free electrode valve acts as a linear amplifier. As a linear amplifier. As a stage with K being 12 to 1.6 and minus sign. It's inverting amplifier. Do you see? Linear, active linear stage. You can tell that you is a rich man at the moment when your living room, in your living, will stand amplifier with this. It's a triode, acoustic triode for 1 kilowatt. Its rated power 1 kilowatt. It's used for still used in acoustic systems, and it's one of the highest possible. When you already have a couple of Maseratis in your garage, you can also have pair of amplifiers with this. This technology isn't energy effective. It's old, energy ineffective, but it's the way to get highest possible quality of sound.
Yes.
This one is demo, this one is real 1 kilowatt. To comparison, it's the same triode but for truly high frequencies. This one is for gigahertz rate. It's also triode. Okay, now this technology considered obsolete, but we have an example of linear active circuit. One stage, nice linear amplifier. Clipping. See, this moment, I'm in this side of characteristic, but because my amplifier is inverted, I have clip on the upper side. I'm in the saturation area. I'm here now. And I have clipping from the lower side. No clipping, linear, I got better point, 13 volts. Linear amplification. Okay, what I'm thinking about. Now, when we solve linear amplifier, let's return to our problem. And our problem is closed loop system. Okay, let's say plus I have a input, I have some kind of linear stage with positive power on the output is greater than power on the input. This one is amplifying. And I have a return, what can be characterized as beta. System with feedback. Output, let's say. And here at the output I have something like back.
Is this one feedback? This
Yeah, lower is a feedback. Feedback circuit. I have forward transfer of amplification coefficient. Here, K is an amplification of the forward circuit, and back is a feedback. For simplicity, why I'm using this ONA, so starting we can try to limit ourselves with harmonic signal, as I do here. Let's assume that we have harmonic signal. It's not very important, just for simplicity. Possible I can put a point here, so these are signal from your basic of electrotechnics theory. Just for beginning. So, for this system, transfer can be found easily. It will be U divided by E. Yeah?
Yes.
This divided by this. Okay. Why? What will we get here? That should be transfer of return multiplied by this voltage. Yeah? If this thing works this way, here is, let's say, input, here is output. So voltage at this point will be voltage, this voltage multiplied by its transfer. Clear? Clear. Because I have sum here, at this point here, what I will get? I will see input plus U back. Yeah?
Yeah.
Yeah. What I will see at the output? At the output, I will see.
U divided.
Wait 1 second. Okay. Transfer of my first block multiply A plus U beta equals to E plus beta transfer of the feedback U. I do have an equation in front of me. I can solve it to obtain voltage U. If I solve this equation, my voltage will be direct transfer 1 minus back Fine? From this, I can write a transfer function for whole system. Transfer function for whole system, I can take it as divided by E, so it will be transfer of the open loop divided 1 minus transfer from the open loop, transfer of the feedback. I wrote it for harmonic signals. Yeah? Yeah. But this part is not dependable neither from voltage, from current. It's dependable only from frequency. It's a frequency function, not time. That's me. But for closed loop system, if I have some kind of, I don't know, Sx from time, if I obtain X from omega as a result of Fourier transform Sx time, output spectral function will be multiplied by or omega equals for any signal. I wrote this for harmonic signal because I have harmonic signal source, it's easy. But it's not limited by harmonic signal. I can extend written to any signal if I'm able to perform a Fourier transform on it. Here I have transfer function of closed loop system. Nothing prevents me from doing one next step. What is the I can switch. So, what is the common form of Fourier transform? Laplace transform. Nothing prevents me from substituting frequency with complex frequency. So, transfer function in terms of Laplace transform will be 1 minus bet and our Laplace images. And output will be multiplied by Laplace transfer function in Laplace space. about the most, how to say, problematic question about such system. It's a question of stability.
It's not stable.
It may be stable and may be not stable, and strange thing may happen. What means stable? And what means not stable?
Stable means like it won't change too much.
I have a better idea to explain this term stable, not stable. If I have ball in the bowl, let's say I push ball up, what will happen?
Come down.
And then return and return and return. So I can push easy, I can push harder if ball is big enough. Anyway, my ball will return to its initial, let's say x0, its initial state. Ball returns to its initial state. This is stable system. It returns to initial state. I can push it, but it comes back. Yeah, I'm speaking about stable system. It's a ball in the bowl. So okay. The salt toy with the weight at the bottom. I can push it. And what will happen? Boom, boom, boom. And comes back because it has what it has. Why it's stable?
Because of
Like-
the base.
Center of mass maybe.
Learn physics. It depends on where the center of mass is relatively to geometric center or center of inertia. Geometric. If it has low center of mass, it will return to its initial state. You can hit it with your feet and it will and come back. And what it's an example of stable system. Stable system returns to initial state. And what about this one? Is it stable?
No.
No, it will fall. Put a weight here, put a center of mass above this geometric center. What will happen? It definitely will fall. This means that it's not a stable system. Now in our case, stable or not stable or what? One second, I'll be back. have idea. We have direct. This is some kind of, I don't know, input. What I'm doing, this is feedback and output. Yeah? Overall transfer being is what? 1 minus input, and all are functions of complex frequency. Now question, will the system be stable or not stable? It's impossible to say already.
Yeah, it depends on frequency.
It depends, yeah. It's the higher radius here, less stable. Higher here, maybe more stable or less. We cannot answer. We need to perform an analysis. Yeah? Yeah. Let's start from idea. And what's the idea? We have some object what can be described with a differential equation. X power n plus a1 n minus 1 x n minus 1 t wait x yes plus a2 n minus 2 x divided n minus 2 times plus a minus 1 x plus a n x equals to 0. It's a differential equation for some complex system, and here variables, what I designated as 6, are voltage or current.
It's like a Taylor series, but it's
No, it's not a Taylor series.
I mean, it looks like
yeah,
this.
but
It goes
it-
infinity, like and
It is not infinity.
Is equal to 0.
No, it goes to 0. It's not infinite. It's a uniform differential equation. For resonance system, it will have 2 members. For complex system, it will have 4 members. For non-periodic system, it will have only 1 member. It's a differential equation for something with reactive element. Yeah, Taylor series approximate some function. Maybe look serious, but it's not a Taylor series, it's a differential equation. For, I don't know, for example, oscillation of something. A lot of systems, not only circuits, physical systems can be described with such equation. Solution of such system, what we will get? Solution is sum where I starts from 1 and to the number AI, initial constants, f power lambda t. And lambdas here are roots of special equation. When I spoke on resonance circle, we saw characteristic equation and lambda 1, lambda 2. Two roots. If they are real, decay, non-periodic decay. If they are complex conjugated, decay oscillation. Where will I get these lambdas? Where will I need to solve so-called characteristic equation? I need to solve A0 lambda n plus A1 lambda n minus 1 plus A2 lambda n minus 2 plus A n minus 1 lambda it's power n minus 1, n minus 2, lambda plus an equals to 0. Power n minus 1, n minus 2, lambda. This is characteristic equation. I need to solve. I need to get roots of this characteristic equation.
You provide this d something over dt like as a lambda.
No, lambda is a root of characteristic equation. What's meaning of lambda? If it's, what can it be?
Like, let me tell you something. In our regulation class, we did all like derivation part. We marked it with s domain, like s. For example, if there is something d over dt,
Yeah.
we marked this instead of s. Is it same? This condition?
Not, they are close, but not the same. This thing is more complex. What are these roots, in fact? They can be positive, real, positive, negative. If they are positive, negative, in time, it's a decaying exponent. These lambdas are characteristic of process. If they are negative, real, we have decay, real and 0, imaginary 0. Process like this. Time, something. Decay. Real less than 0. Imaginary greater than 0. Decaying oscillation. Real greater than 0. Kaboom. System will destruct. Not stable. Actual lambda. What we saw on resonance circuit, what was lambda? Resonant frequency. Lambda, it's O decay constant of decay, in its real part. or frequency of oscillation in its imaginary part. Roots of characteristic equation.
And they both together call it S domain, yeah? Like lambda plus imaginary part. Which
No,
is
it's always kind of real imaginary. But wait. Did they spoke on system state? Because lambdas are in frequency space. Lambdas are in coordinates. But omega constant. It's a coordinate space for lambdas. Real part of lambda is C from Laplacian transform, and imaginary is frequency from Laplacian transform. System estimates are in coordinates signal, derivative of signal. You're not confusing them. Because there can be a coordinate system where here is, let's say, S from the, and here the S from the, by the. You can operate in such coordinate space. Okay, we are at high level in the space of complex frequency. How to say, cornerstone of stability. If you have lambda 1, lambda n, and a real part of all lambdas from 1 to n is negative, your system is stable. This means what under any external impact, system will return to its initial state. By this way, or by this way anyway, it will return to its initial state. If you have one unique lambda with positive real part, your system is not stable. What is characteristic equation? Actual characteristic equation is a divider of transfer function. Divider of overall transfer function. This means what's a lambda? Coordinate space. Point when lambda goes to infinity. It's a point when one not right. It's a point when 0 at this lambda goes to infinity. This is correct, sorry. Polar. Remember such idea, polar of complex function. There are zeros, points where complex function becomes 0,
Poles.
and polar.
Poles, yeah.
Pole is a point when complex function goes to infinity.
Yeah, maximum, infinity.
Roots of characteristic equation are points when divisor of transfer function becomes 0 and transfer function goes to infinity. Добрый день. When boss calls you, you need to answer. How many students will we take next year? As many as we will be able. to anyone who can understand complex frequency. Okay, what I'm going to write? Let's say we have some system under the influence of the external EMF. It's my hammer. I'm hammering my system with external EMF E from T. And X is output. Here, this X from the differential equation, see, this theory written in a kind of common form. In our case, we have system with something inside this way, back way, something. But here, this, how to say, process variable, X, is output voltage. If we do so, we can write an equation, I hope. So, A0, sorry, it should be derivative. And derivative plus A1 and minus 1 derivative from my voltage and minus 1 plus A2 and minus 2 derivative of my voltage plus and minus 1 from time and plus here should be an not a derivative equals to E. Yeah, that's what we will get. We have simple system under influence of one EMF. For simplicity, let's assume zero starting condition. Let's assume something like, one moment. It's for simplicity, we are interested in free, so here is my from time. Let's assume that it's reached at 0. My system output my voltage. Should have ground somewhere.
Professor, is this in this cloud? Is there amplifier inside?
Yeah, it's amplifier with feedback, etc. It's my system that can be described as differential equation. I just use zero condition for simplicity. But yeah, inside is everything, all, it's active, it's fully active. But there was no input in negative time. So in Laplacian space, my differential equation will become A0 lambda power n plus A1 lambda power n minus 1 plus A2 lambda power n minus 2 plus n minus 1 lambda plus an equals to what's here? E is a Laplacian transform of my input, Laplacian image from my input MF, and is a Laplacian transform of my, let's say, output voltage, observed voltage. Now I can write what? I can write my transfer function. It will be divided by from equals to 1 divided by A0. I can put a frequency here. Plus A1 1 plus A n minus 1 t plus A n. I can write it in this form. All lambdas. I will have roots lambda 1, lambda n. These roots are places when divided becomes 0, or points when divided becomes 0, or polars of transfer function. And system stable if real part for lambda e that from 1 to n all are less than 0.
Professor, why I understand this part, but why for u part we just write 1 only?
Why? Because we have polynomial a equals to u. Polynomial start form a lamb or a p.
Yeah, I got it. But not why there is not only polynomial, but there is a 1 divided by 1 over by polynomial.
Yeah.
Not polynomial, just so. I didn't get this.
To get from Poland, what are you doing? You divide by it. So you will get u divided. You want to get u transfer function output divided by input.
Yes.
Divide by polynomial, you get u divided by polynomial. Divide by e, okay. You need it in form u divided by e. Okay. Or not okay. So we can expect that system will be stable, all process will have decaying character if it has no pores on the right side of the plane. Let's say +1 here, omega. If all lambdas are here, stable, maybe better in green. So if all pores are on the left side, this is area of stable system. If you have one lambda here, not stable. On the right side, or on the pores on the left, stable. One on the right, non-stable. I would like to illustrate it. I would like to illustrate. I will use system. Electron valve. Well, not important capacitor. One, two. Ground. This will be plus 250. And set. Oops. this pair will be coupled by mutual inductance. My idea. I would like to use this network theoretically, I'm able to use some kind of S6 here to apply an input. Ground. Yeah, such kind of network. It's an amplifier loaded with resonance contact and feedback in the form of mutual inductance. Okay, I'll need some time to assemble it.
Maybe you can.
Yeah, you can drink your coffee.
Professor, is this so? This PCB of
This is PCB, it's a protective device, quite old. Our development, it was fault recorder, distance protection over current protection. These two are program memory, is what you're looking at. This one is non-volatile memory. This part, analog to digital converter and amplifier and multiplexer. Input channels, program memory, RAM, operative memory, non-volatile, processor itself, and this was to drive outer memory module.
can you tell me
This one, input filters to suppress Nyquist frequency, protective diodes. This one,
digital?
no, it's not an ADC. This one is multiplex, channel selector. This one, controlled amplifier. It's extension of ADC array here. This one is ADC.
You said something like digital last time. I forgot what
It's an analog to digital converter. Input signal from this part, scale, currents and voltages go here. Here they are transferred to digital form. It's this one is ADC, and processed by this signal processor.
like this ADC is, for example, in our last semester we had basic digital electronics,
Yeah.
and we worked with gates, logics.
Gates logics here, and this one analog to digital converter, like automatic voltmeter. You give at input is a voltage, at output is voltage measured in it's integer being voltage measured in relative in per U. And the second board, communication or something that, and these two NVRM, external NVRM module. It also had display, but I don't know where this display module is. Somewhere. It's somewhere.
Do we gonna study this more closely in an embedded system course, I think? Yeah.
Something like this.
code we gonna
Some not protective device. You're on an adaptronics program, on
Yes.
an adaptronics. Something like a MSP, yeah, embedded device. Something like this shouldn't be.
we gonna do it in next semester?
I can tell. I don't know precise electronic program. I don't know your planning. Honestly, I forgot it. It's normal. Don't worry. Okay, what I need a decoration change. I will do some decoration change. It will take some time. This is nice trivial, but it looks nice, but characteristics are not so good. I need one with
What is this behind you? Like something looks like mechanical.
but then it's phase shifter. Actually, it's a phase rotor machine. It allows to obtain secondary voltage shifted plus minus three-phase system of secondary voltage shifted on any angle from plus 180 to minus 108 relative to primary system. See, I need, for my next class, I need good symmetrical 100 volt system here. But this transformer is a bit damaged. It was in students' hands, and it's not fully symmetrical. I want to use this guy to get one ideal, close to ideal 100 volt system. But I need to assemble its control panel. All this for, I will assemble all this in one, I hope.
Professor, let me show you what I told you in middle of class. Like in our previous semester, in our one course,
Time be from x from time.
yeah, we did it like as a S.
In theory of signal, it's not a good idea.
Like, and there is something looks like this, and S plus something like this, yeah.
No,
Or-
something
no.
definitely wrong.
I
No, it's a form, appears what it should be a form of Laplacian transform. Because the is should be in this way.
yeah, in this.
And it's the same P C plus J omega. It's another form of compact frequency. And appears what do we know about Laplacian transform? Theorem, I pointed with my finger. If you have some x being function of time, you perform a Laplacian transform on it. Sorry, it's x. What you get? You get it in the space of compact frequency.
Yeah.
Now, perform Laplacian transform on. And what will you get? Px plus x from initial condition. That's what it's talking about. Substitute it's two forms of writing this Laplacian frequency.
Yeah.
P and S, there's no difference. It's a constant plus complex omega.
And because of this, let me, which is Fourier transform,
But you
which is
wait 1 second.
This is exactly Laplace.
No, it's
transform.
Fourier transform.
I know, like,
Substitute.
like it's when it is. Okay, I'm gonna write it Laplace when it is, but when like.
No, something goes wrong.
Let me complete it. When this one is 0, when this one is 0,
Oh.
it's equal to Laplace.
Wait,
Fourier
1 second. No, not so easy. Not so easy. Yes, when you substitute, if you have image in Laplace space as a function of complex frequency, and you substitute complex frequency with your omega, you will get spectral function, a result of integral Fourier transform. Yeah?
Now, I thought like because of this one, when this one is 0, we're gonna write only this one, which is in Fourier
Come
transform.
on, open my previous lecture.
Okay, I'll see. Let me do.
Yeah, it's my previous lecture, Laplace transform. Laplace transform is a common form of Fourier. It's an extension of Fourier.
Yeah, I think what I'm saying is also a little bit looks like this. Laplace is common form of
Yeah,
Fourier, and Fourier is
Is-
also Laplace when it is.
Yeah, and Fourier, spectral function in case. See, there is Fourier transform for periodic signal, that's what Fourier himself wrote. And integral form of Fourier transform. Integral form of Fourier transform is a version of Laplacian transform. Yes, it is. They are all members of one family. But first, Fourier transform was developed, and then Laplacian.
Like first.
Yeah, in Laplacian transform, there also is one more, Carson-Heaviside. If you would study in United States, possible that you will deal not with the Laplacian, but with Carson-Heaviside transform. Difference, if you have Laplacian transform, for example, x, capital from P, in space of Heaviside, it will be Px, not P. Complex frequency multiplies. Okay, I want to do something. Need to do something. I will assemble next network in some 10 minutes. It will be funny, complex network. Disassemble. I hope I can. Disassemble everything. I will use this. Well, it's give me more amplification. Chaos attacking. Okay, this is my positive, and this will be my ground. Now, resonance part of that. My coil for resonance circuit, and this one for grid. It will be feedback. And play my capacitor. Ground. I need a good ground here. I need a good ground. Maybe you will be my ground for today. And that's not all. One moment, I'm pointing. Yeah, it would be better. this will act as a voltage limiter. Because I'm expecting quite high voltage here. Maybe divide. Or left like this. Bit coil, smoke coil. What about here's my ground and this one can be my signal. I'm waiting for students. Schematic is here. Ready for schematics. Come on, machine. My students. students. Circuit is waiting. Welcome. Okay, what a nice circuit I have.
This one is, yeah, this one is, you know what is E? Graph of E, you know how it's, graph of E, it's like this.
Okay, I see.
This.
What a circuit I have. In previous years, I tortured with the manual switch. Today I'm lazy, and instead of manual switch, I will use pulse generator. Is point A, is point B. I have this network, linear amplifier, loaded with resonance contour. And feedback with mutual inductance. Here is my capacitor for my contour, here is my coil, and this one movable is a coil of feedback. They are coupled with mutual inductance. It's my system. One more element, I add this neon lamp. It's a voltage limiter. It has active resistance inside. It's a voltage limiter. It's needed. I don't want to burn everything.
So it's like a voltage divider or something?
No, it's voltage limiter. At low voltage it does nothing. Its voltage is high enough, gas discharge appears, and it will take energy from resonance circuit, then transfer it to heated line. It's a limiter. I need something like this. Limiting function. Better. Like this. Current limiter. Okay, here is my circuit. What's inside? I have active element, my electron valve. Anode current, something like this. Delta H. Valve of anode current. Valve effectiveness can be characterized with so-called stiffness. It's delta A divided by delta A graph. It's milliampere per volt. It's a characteristic of its amplification capability. Understood?
Yes.
Yeah. In my network, in the network I have assembled, I can show it as a direct transfer beta here can be approximate. It's not 100% precise, but can be approximated as my stiffness multiplied by input resistance of my load as a function of frequency. Beta will be in somehow nothing else than metal inductance divided by inductance of contour. Who's here? At the input, I will use small pulses, 1/2 of microsecond within 3 milliseconds, something like this. But it's not important in this moment. What's important? What's important? My input resistance of my load of this network, input resistance of this network can be written AB. Frequency can be active resistance. It's an equivalent loss of in coil and in capacitor. Capacitor loss are important. I can prove it. 1 plus R omega capacitor plus 1 divided by your omega inductance. I can write it in terms of Laplacian transform. What will I get? AB as a function of Laplacian frequency will be L divided 1 plus L P ck plus 1 divided by P hk equals 1 divided by contour resistance divided by p square plus 1 divided rck p plus 1 divided ltck. Simple transformation. What we will get? 1 divided by contour capacitance frequency p square plus double alpha p plus omega 0 square.
Professor, is it still transfer function?
It's not, it will become transfer function. Now it's image, Laplacian image of this part. It's a lot of, but it's one tiny moment. This part is linear. It will be only factor. Frequent, why this experiment done like this? Linear part, simple minus stiffness, and a resonant part. This part gives me unadaptable, absolutely defined frequency characteristic, frequency response. I have this HC to get it's a resonant circuit with absolutely predictable frequency response. We saw it in the resonant circuit 2 lectures ago. Yeah? Resonant circuit. First part.
Yeah, resonance.
Yeah. Decaying oscillations with decaying factor 1 value here. This one goes decaying decrement, and this one is a square of oscillation or resonance frequency.
So
Yeah.
It means like in resonance frequency, this tends to steady state.
This tends to that independence of a return. It will now it's stable. See what happens? We saw image like this, no? 2 lectures before. Free resonant contact, free. Maybe wait. Oh, come here. I'm changing inductance. Oh. I'm changing frequency of free oscillation. Again, AB can be written as 1 divided by CKP p square plus double alpha p plus omega 0 square. Now, transfer function. This is frequency dependent part. Now, transfer function itself for my system will be okay. I will cut a bit. 1 minus divided by p squared plus double alpha p plus omega 0 squared multiplied by 1 plus beta s c divided by p squared plus double alpha p plus omega 0 squared. Oh, here it is. Here I have my transfer function. Now it should be simplified. With kind of simplification, my transfer function will be minus s divided by ck p frequency square plus double alpha plus p yeah, write better correctly, divided by ck p plus omega 0 squared. Here it is. Alpha above LC from resonance circuits and omega 0 equals to 1 square root ck. Here is transfer function. Very simple. Overall transfer function of the system. I'm a bit simplifying. Here is my return.
Professor, yeah, it looks like you derived voltage resonance frequency formula. You derived it.
No, bit different. I intentionally use network with one resonant frequency to get determined characteristic. I can use a different network, but I need predefined known frequency characteristic. That's why I use resonant, because we knew this characteristic. I can use more complex. I can take what kind what's we have on our shelf? Non-periodic system, second order system with one resonant frequency, or mutual coupling with two resonant frequencies. Yeah. I choose resonant because we know how it responds and it's predictable. Non-periodic will not. The problem non-periodic is not so, how to say, it's not so obvious with its reaction. This one is better. Yes, I intentionally use resonance system. See, I need system with known open loop equation. Okay, one point here. My linear part is inverting. If you saw one scale or one or single triode amplifier is inverted. It has a transfer factor with a minus sign. So, at the frequency omega omega 0, so at the point of resonance, will be minus SR, mean it's less than 0, negative. So that's mean what if beta equals to plus, if beta is positive, this means what overall return will be negative. If it's minus, I will have positive return. Clear? Let's take bet plus m divided by AK. K is m and inductance of this coil is AK. This to analyze case of negative feedback. Now it's set for negative feedback. Our system transfer function in case of negative feedback will be minus S divided by CK, P divided by double alpha plus MS omega nullus square P plus omega 0 square. We need to solve equation. This one equals to 0. We need to solve, to analyze stable or not stable, we need to solve equation divider equals to 0. What we will see? Lambda 1, lambda 2 will be minus alpha plus ms omega 0 square divided by 2 plus minus yep, square root omega 0 square minus alpha plus ms omega 0 square divided by half. Here are two roots of my characteristic equation. What do we see? First, both roots are negative. Equals always stable. System always stable. And second one. See this? The higher M, the higher motor inductance, the more stable system should be. Can you believe me? like to check what happens. Where am I? Come on. Okay. LT coil of feedback. Maybe I change. Sorry. Here, I can. You see, we have decaying oscillations with frequency omega 0. 1 second. Oh. Inductivity increases, frequency decreases. Very nice. I'll take a bit different time scale. What will happen if I increase coupling?
Increase what?
Coupling.
Which
If I increase M.
Mutual index?
Yeah. Look what happens. See? It acts like damping. Small coupling, small mutual inductance, high coupling. System become more stable. It's like making this ball deeper. I can do things like this. Oops. Small coupling, higher, higher. See, negative feedback makes my system, like damped, more stable. It returns to 0, to its initial state, at any coupling I can raise. Oh, here it is. I can put a screen here, close to this. Couplet. I can play.
Are you increasing current with this one?
I'm reducing air. See, playing with the area of lanes involved, I change quality of contour, amount of losses. I can put an resistance in series. One moment. One moment for comparison. Where is my resistance box? Resistance box, where are you? I saw you hiding.
So how do you call it? Like resistance?
This one is resistance box. They have the resistance box.
Like it's potentiometer.
You need second one to use the potential. Now it's simple rheostat. It's a set of precise resistors. See? I increase resistance, as we saw it in 2 lectures before. One moment, I can make case above critical, it's a near periodic system. Nothing changes. Increased negative feedback makes systems stable. Same way, like this. I increase losses, system stable. Okay, this one is with negative feedback. So, negative feedback makes system,
More stable.
yeah. Once more. No feedback, small feedback. Oh. Negative feedback makes system more stable and more linear. Okay, let's see what will happen in opposite. I can do what? What can I do? I can try positive feedback. I will see positive feedback in case of that being minus m divided by 8. I need to turn coil this way. In such case, I will have what? I will have again 2 lambdas, and they will be minus alpha minus ms omega 0 squared divided by half plus minus dot square root of omega 0 square minus alpha minus ms omega 0 square divided by half. Oh. Something wrong? Yeah. Oh, now it's okay. This part is a frequency of expected oscillations. This part will give me frequency. And what about upper part? My system is stable while this one is greater than 0. system is stable via alpha minus ms omega 0 squared divided by half greater than 0. Or I can rewrite it R is less than L divided by ms.
Professor,
Serious?
Professor,
Yeah.
I'm still didn't understand what is this alpha.
What's meaning of
Alpha.
alpha? Alpha is a decay. See what happened with oscillation?
Yes.
Alpha 1 divided, F divided by C. If you connect all these points, you will get a power minus alpha t. Alpha is a decay.
Yeah, I got it. So if it's like I can't remember. So if alpha is power of e to the power, then this other thing is also power, yeah?
No.
We are
In
dealing with
alpha,
power.
we have process, very simple, capacitor discharge. A minus alpha t. Alpha is a constant of decay. Decaying oscillation. This line is A minus alpha t. It's a decay factor or Grimsham's constant. Decay constant. How fast process goes to zero?
Yeah, I got it.
I increase alpha with the increase of resistance.
So if you
Decay
increase,
is faster.
that means it goes to zero faster than.
Yeah, the higher alpha, the faster it goes to zero. Okay. Let's see. There's one more moment. If you can see omega 0 place, I can see I'm changing capacitance, but it also changes timing of process. Okay, let's select something like this. Can we see it? One moment. One moment. We don't see coils.
So if feedback is positive,
Yeah, now let's try to.
it must be less to
Yeah,
be more-
it's a criterion of stability.
yeah.
If this fulfilled, system stable. Now it's fulfilled. You see, system stable. Increase M. Less stable, but still stable. Change. Very virtual, no positive feedback. I'm increasing positive feedback. Increasing. Come on. I'm on the brink. See how long, but it's still stable. I can. Still stable. I'm on the brink. stable, system no longer stable. Oops. I shifted coil. Stable, less stable, less stable. Here, a bit more. I'm gonna bring up. Still stable. See how long is the case? I'm on the edge. Up. Not stable. And if I increase, need to. It's become a generator with a frequency omega 0. Now it's a stable generator. Because I have a current limiter. See? My neon acts as it's a limiter. Without it, at this moment, voltage, it can reach 200 volts, something like this. Okay, 191. I can see for bigger one. More obvious. It's a stable point. 200. It reached 200 volts without limit. In theory, without any limiter, it can be infinite. Of course, it will not be infinite in reality, but it can reach very high values. And here, I've increased active resistance. I've added 20 ohms. Non-stable. Stable, not stable at all. With the plus 100 ohm. What? See, with added active resistance, system more stable. Ohms.
So if feedback is negative, it's much more easier to be stable, yeah?
It's guaranteed stable. If feedback is negative,
It's
it's solid rock stable. With positive, you always see an edge. Problem, what in many cases, you need positive. Voltage stabilizer or something like this. On the brink of stability. Maybe. On the brink. small, oh, not stable. Difference 2 ohms. I'm decreasing active resistance. Not stable. Stable. So here criterion includes frequency, resistance, all here. I can play with inductance. Increase. Increase of inductance make it a bit more stable. Okay, you saw it. Stability criterions, I will left them to the control tower. There are several ways how to determine stable or not stable without solving characteristic equation. Rouse, Nyquist, Gurwitz, it's for control theory. I will let it to them. With the positive feedback, my circuit become a harmonic signal generator because it has response on one frequency. Now it's a generator of harmonic signals. Questions? If no questions, I can prepare for red button. Where is my what I need? What I need? I need this one. I need my resource access to resource planning system. FPS. Okay, I see no questions, so I will end the stream for today.